All right. Good morning, everyone. Thank you all for coming. Unfortunately, an early time, but all that managed to work for everybody. I am giving my master's defense talk on an introduction to exponential random graph models. We'll start with an overview of the basic graph theory, and then we'll start talking about the characteristics of the model itself. Then we will move into certain graph structures that can be used. And then there'll be a brief primer on logistic regression. Once we have defined the model characteristics, graph structures, and logistic regression, we can actually go through a process where we derive the original model equation. Then I will be discussing the way models are fit briefly, then provide a few worked examples, and then the results of a simulation. Here is a very brief introduction to graph theory. So we say that a graph V, or a graph G, is a set of vertices and edges. And vertices are our entities within the graph, and edges are connections between vertices. You end up having similar terms that can be used. So vertices are also commonly referred to as nodes, and edges are also commonly referred to as ties and dyads. There are more terms as well. Edges can be undirected, where they just exist between two vertices, or they can be directed, where they extend from one vertex to another. One of the two common ways to store a graph is in an adjacency matrix, which is given here. The other common way is an adjacency list. And so we can see that the vertex 0 reaches a 1 here, and therefore there exists an edge between vertex 0 and vertex 1, and 0 and 3, and so on. We also, because this is an undirected graph, have the property where we can go down here as well. We have a diagonal or symmetry across this diagonal line because of that. And note that the diagonals here are 0 because in this context, we cannot have an edge that goes from one vertex to itself. You can in other uses of graph theory, but here that does not exist. If you have directed graphs, then you have the source listed here and the destination listed here. And you lose the symmetry unless every edge is reciprocated. Right now, we're just using 0 and 1 to denote the existence or lack thereof of an edge. It is also possible to place numerical weights, and there has been work done to generalize exponential random graph models to have continuous weights. That is, however, beyond the scope of this introduction. And here is the exponential random graph model itself. So here, Y is any possible graph on the vertex set, meaning that we have a set of vertices that we consider fixed, and then we look at all possible sets of edges that can be applied to that graph. Then we say that the probability that any particular graph exists is proportional to this expression with the exponentiation of theta transpose z of y. And theta transpose z of y is our linear model, basically, for the parameters. And so if we give an example here, this is taken from the first example where theta is just a negative 1.69. And the z of y is just the number of edges in y. So in this example, we say that the probability that a graph equals a particular graph is proportional to the exponentiation of the graph density parameter or edge density parameter multiplied by the number of edges. And note that this probability is proportional. If we want to get the probability equal, then we need to find a normalizing constant. And unfortunately, those normalizing constants in all but a few examples end up being intractable. So if we have 10 vertices, there are about 35 trillion possible graphs. And it scales with this expression, 2 to the n choose 2. For an undirected graph, and this scales incredibly, incredibly quickly. And before long, we're getting to the point where we send a computer back to the Big Bang and look at it now, and it's still running. And so as a result, methods are needed to get around the intractability of the normalizing constant. Now we'll go into some notation used. And so we will suppose that we have an undirected graph y, and yij will be the relationship between I and j, which are distinct vertices. And so if an edge exists between the two, then yij equals 1. And if an edge does not exist, then yij equals 0. When we have these terms here multiplied across, if we have a 1, that means that all of the elements here are 1. And if we have a 0 when we multiply across, then that means that there was at least one element that is not a 1. These examples are only with 2, but they can get longer. The degree of a vertex is simply the number of edges that connect to a vertex. We end up getting a little bit different for the directed graph. So if we say we have a directed graph y, yij says that we have an edge going from I to j. However, unlike with an undirected graph, we cannot also say yji equals 1. And the definitions of degree end up being pretty similar. The in degree is how many edges are coming in, and the out degree is how many edges are going out, about what you would expect. And so we'll now go to the basic graph model, where all edges are independent and have the same probability of occurring. This ends up being used when we're doing model fits as the null hypothesis, where you start with, okay, let's not even look at any other features of the graph. We're just going to say every edge has the same independent chance of occurring. And in this situation, the total number of edges will follow a binomial distribution. And here we have theta is the density parameter and z of y is the total number of edges of y, which corresponds to the example given here for the simplest case. Now that we're here, we'll talk about various graph structures, and we'll start with undirected graphs. And so, while it's possible to treat every edge as independent of the rest, that ends up not being realistic a lot of the time. And also, a lot of the time, we're interested in understanding the edge dependencies. We want to know what structures are likely to occur and likely to form. And so this represents more complex relationships. And so we can start with the total number of edges, which is just the edge density parameter from before. And then we can move into what is called a two-path, where yij, yjk equals 1 right here. The clear extension of this is the triangle, where yij, yjk, yki equals 1. We can also define a cycle of any length. So this is a cycle of length 4. Another possible statistic is the triangle percentage. So we say how many triangles can exist, what proportion of those do exist. And there are many, many, many more structures that could be used. These are just a handful. We can also have data on the vertices themselves. So in the second example I will be going over, the data corresponds to high school students in a simulated network. And so each high school student has variables attached for grade, race, and sex. And we can end up defining statistics based off of these attributes. The simplest is just the mean degree of all the vertices. We can also look at the k-stars and the individual degrees. How many vertices exist that are degree 0, degree 1, degree 2? And these are relational statistics based on how the vertex relates to others versus the variables directly on it. So we can have categorical variables. And homophily is how many edges occur between vertices of equal values. So with that high school set, it will be how many edges occur between people who are the same grade, for instance. You can also just count the individual values and use that as a parameter as well. For continuous variables, you can look at the absolute difference between vertices, and you can sum between two vertices as two possible statistics. You can also work with other functions of the vertices, but you cannot just directly subtract because this is undirected. You don't have a direction to do the subtraction in. So whatever operation you use has to be commutative. Now we'll move to directed graphs. We start again with the total number of edges, and then we can look at asymmetric relations. And this is a case where we have two vertices with precisely one edge between them. The obvious counterpart to that is the mutual relation, which is how many cases do we have two vertices where there is an edge that goes in each direction. Activity is defined as yij ik equals 1, and popularity is defined as yji ki equals 1. And clearly, you can define these with larger numbers as well. Triangles end up looking about the same as before. You just need to be able to follow the arrows in order to get back to where you started. And again, you can have cycles of longer lengths. And there are many, many, many more possible things that can be used. Transitivity structures are very common in looking at social data, but just don't have time to go into all of that. The vertex level attributes for a directed graph end up being pretty similar. Homophilia is defined as before, factor effect is before. You can do the mean degree, you can depend on the out degree and the in degree. When you're doing continuous variables, though, as opposed to doing the absolute difference, now that you actually have a direction, you can just take the difference between the values. Now we will start defining odds and log odds. So let us say we have a probability P, so that is bounded by 0 and 1, and we will attach the additional condition that it is not 0 or 1. We say that the odds of P are P divided by 1 minus P, and the log odds of P are the natural logarithm of the odds of P. And what log odds give us is a linear model for probability. So we can directly add and subtract log odds of various events, as we'll see in worked examples, and then you can convert them back to probabilities. Now we're going to do a very, very brief introduction to logistic regression, which is a generalized linear model for binary response. So you would say that a probability of a certain occurrence equaling 1 is equal to the exponentiation of your multiplied linear model. This is equivalent to the theta transpose z of y. The notation is just, this is just the standard notation for logistic regression versus the standard notation for exponential random graph models. And so it is the exponentiation of the beta transpose xi divided by 1 plus the exponentiation of the beta transpose xi. And if we look back at this, we can observe that this is how you move backwards from log odds. So you take log odds and you put them here and here, and then you get a probability back out. This also has the convenient feature of the domain for this is the whole real number line. So any possible real number, whereas the range is just 0 to 1. So we can map any real number to a probability this way. The fit for this is usually done with the Gauss-Newton algorithm for iteratively reweighted these squares. I'm not going to go into more detail on that here. So now that we have all these parts, we have the notation, we have logistic regression and all that, we can go back to develop the actual model. And at this point, I was getting somewhat sick of the ability for Google Slides to format equations. So I formatted them elsewhere and screenshotted them in. So we will assume that the probability of a particular edge occurring is the exponentiation of theta, which is just a number right now, over 1 plus exponentiation of theta. And therefore, the probability of the edge not occurring is 1 over 1 plus exponentiation of theta, and therefore the probability of occurring and not occurring adds to 1. Now we will define the binomial random variable, which was mentioned earlier. So here we have n independent samples, and each of them has the same probability of success, and this is the probability mass function. And so what this represents here is p to the k represents the probability of getting 1, 1, 1, 1, 1 up to k ones, and then 0, 0, 0, 0, 0 up to n minus k zeros. And that is the probability of that particular sequence. Then when you have the n choose k, that tells you how many ways you have to order those. And so that tells you the probability of getting that many successes. Now we take these values here for probability and we plug them into this equation and we get this. So the n choose k starts with n choose 2 for n because there are n choose 2 possible vertices that can occur. And then we're choosing k of them. And then when we plug in the rest, this is the expression we get. Then we say, okay, what is the probability of getting a specific graph that we will call yk, and therefore it has k edges? The probability of getting that graph is the probability of getting a graph with k edges divided by the total number of graphs that have k edges, because in this situation, all of the graphs with k edges are equally likely to occur. This is developing back to our basic edge-only model. Then we substitute in the values we found from before, and we get this term, where exponentiation of theta to the kth power, and then 1 over 1 plus the exponentiation of theta to the n choose 2. And theta is just a parameter in this case, so this whole denominator is just a constant. And therefore, we can take the equality here, we can get rid of the constant and say it is now proportional to the explanation of theta k. And then this takes us back all the way back. We have now developed the basic edge-only model based on independent logistic regressions. Hopefully that made sense. So when we have no edge dependencies, so no triangles, no two stars, nothing like that, we just use logistic regression to solve graphs, because in that case, the problems are simply equivalent. And you can do vertex level attributes while still doing logistic regression. However, you cannot do logistic regression when we have edge dependencies. And so when we have edge dependencies, we have two methods for doing estimation. The first I'll be talking about is maximum pseudo likelihood estimation, abbreviated MPLE. And so here we are conditioning each edge on the rest of the data, and we're just kind of ignoring that the dependencies exist. And this ends up being pretty straightforward to implement, and you can run it quickly with complex models and lots of data. But the problem is that we're ignoring this feature that we know is in the data, and then this comes with downsides. So the MPLE estimator has properties that are just not very well understood, and there are known data sets where the true parameters are known that it tends to perform pretty poorly on. And then that brings us to the next method I'll be talking about, which is Markov chain Monte Carlo. And this ends up usually being implemented with the Metropolis or Metropolis-Hastings algorithm. And a brief description of how it works is you start with a base graph, which is often the empty graph. And then you take random vertices and you alter the relationship between the vertices. So if we're doing an edges plus triangles model, then we might grab two edges and either add a vertex if a vertex does not exist, or we might remove a vertex as one is there, or add or remove a triangle. Then this gets compared against the observed graph, and the more similar it is to the observed graph, more likely it is to be accepted. Otherwise, there is a chance that it can be rejected. And so you do this enough times, and ideally, you start getting a series of observations that correspond to the probability mass function of the graph. And the parameter values are estimated by changing initial values for the parameters and seeing how close the graphs get to observed data. MC methods do tend to have their own issues as well. It does not run nearly as quickly, and that particularly with over 1,000 vertices, this can become a problem. There's also an issue with graphs that end up being multimodal, meaning that there exists local maxima. And given that our process involves looking at whether or not we change at the time, we can easily get stuck in a local maximum, and that will prevent convergence. And that'll give us a really, really bad sample, and that's going to really screw up our inference. It's also possible when you're simulating to get a simulated graph that looks very little like the observed data. And this ends up preventing coherent results. This is more common when the model you're using doesn't actually match the data. So if you try to match triangles to a data set where triangles don't exist at all, or where they're rare, then you're going to start simulating a bunch of triangles that aren't really represented, and therefore your simulated graphs are going to not look really anything like your actual graph. Still, however, MCMC is preferred to MPLE, and there is active research being done on how to deal with all of the issues here. Now we're going to get to the first work example I did, and this is a data set of 16 Florentine families from the Renaissance, and these are mercantile families. So here, each vertex is a family, and each edge is a marriage between families. There are 120 possible edges, of which 20 are present. And so when we fit the log or the edge-only model, we get the log odds of an edge occurring of negative 1.69, which translates to a probability of 1/6, which makes sense. This is what we would expect to get. If we're only looking at the chance of an edge occurring, and you have 20 edges out of 120 possible, then each edge has a 1 in 6 chance of occurring. Next, however, we're going to try to look at the triangle parameter, because as we can see, we have a number of triangles here in the data. And so if we have a negative triangle parameter, then that would mean that triangles are less likely to occur than you would get by random chance with independent edges. Meanwhile, if you get a positive triangle parameter, then triangles would be more likely to exist relative to independent edges. And we end up fitting it to it. And so here, the log odds estimate for one edge ends up being a little lower, which is one, we have another parameter, but also now that we're using MC, the results are stochastic. So you will get a slightly different result each time. And so if we go back to our model, theta consists of two components, theta 1, which is our edge parameter, and theta 2, which is our triangle parameter. And z of y will be the number of edges and then the number of triangles. And so we get the log odds of an edge occurring are negative 1.67 plus 0.16 times the number of triangles created. Now that we have edge dependencies, we can no longer consider edges independent. So when we talk about the log odds of an edge occurring, that is conditioning on the rest of the graph being in some potential configuration. So we look at one possible edge and we assume that every other possible edge is determined and fixed, either existing or not existing. And that means that if we have fixed every possible edge except one, then the log odds of an edge occurring in that case are negative 1.67 if by adding the edge, a new triangle would not be formed. That is to say, the probability of a marriage occurring if it will not complete a triangle is 0.158 approximately. However, if we are forming one new triangle, then the log odds change and we have a 0.181 chance. We can also, by adding one edge, create two new triangles. And then this would give us a higher probability. So if everything else is fixed, the probability of a marriage occurring between two families, if it would create two triangles that did not exist before, is approximately 0.2. And this is the next example I'm doing, and this is the high school data from earlier, and this is a friendship network. Note that this is an undirected graph, although I have heard compelling arguments for why friendship networks should be demonstrated as directed graphs. And so we have about 1,400 students here, and this particular plot is color-coded by grade. And just looking at it, we can observe that there is a substantial amount of clustering based on grade, which is what you would expect when grade moves from 7 to 12, as it does in this data set. And we also have the other variables of sex and race. So let's start with the edge-only model that we always use as the null hypothesis. And then we look at the probability of an edge occurring with log odds, which is, of course, just the proportion of edges that occur. And now we're going to try to match with these. So we're going to try to look at the sex, grade, and race and see how those interact. So theta 1 is the edge parameter, which is just the density of edges as before. And then the first element of z of y will be the number of edges that occur. Theta 2 is grade matching. So it is the number of edges that occur between students that are of the same grade. And race and sex are defined similarly, and then z of y is just the counts of these. And so we can observe that when we look at this full model, the log odds of an edge occurring if none of the characteristics match are quite low, and then matching on any of the characteristics will kind of give an improvement to the log odds. And now we need to do some model comparison. There are a number of ways to compare models, such as the likelihood ratio test, AIC or BIC. I will just be using AIC here for simplicity. And so AIC is based off of the log likelihood of the data, and there's a penalty for parameters being applied to prevent overfitting. And so we can see that the AIC for the simpler model is about 15,000, and the AIC for the full model is about 13,000, and lower values are better. So we can see that the full model is about 2,500 lower, meaning that it is a vastly improved fit. And for the third example, we've been looking at the Sampson's monks data set. Sampson was a researcher who was polling monks on who their favorite other monks were in the monastery in 1969. There ended up being 3 different sets of observations taking place at different stages of political drama within the monastery. This comes from the third observation. And here, now that monks are being asked to pick who their favorite monks are in the monastery, edges are now directed, which means that we have twice as many possible edges. And so if we start by fitting just to the edge density parameters we did before, then we get the log odds of an edge are about minus 1.5, and the probability of an edge occurring is about 0.183, which is what you would expect. This is just the proportion of possible edges that exist. But looking at this, what if we want a little bit more? What if we want to look at whether or not they're more likely to list a monk as a favorite if they're listed in return? And then that takes us here. So when we make the full estimate, we have theta1 as our edge parameter, theta2 as our mutual parameter, and then we have the probability of an edge occurring is about 0.1 if there is not another edge. If there is another edge, you add together these log odds, so that'll be the log odds of an edge occurring, and with the log odds of it is matching another edge in the opposite direction, and then the probability rises to about 0.53. So then the interpretation of this is if monk B does not have monk A as a listed favorite, the monk A only has about a 10% chance of listing monk B as a favorite. Meanwhile, if monk B does list monk A as a favorite, that chance rises to about 54%. And we get a substantial drop in AIC here, which tells us the full model is superior. A common rule of thumb is that a difference of 2 in AIC is statistically significant. Now I will move to the simulation I performed. So I took the Florentine edge-only model and simulated 200 times, which means that this was 200 binomial draws with 120 possible edges and a probability of each one occurring of 1/6. And so the actual model is proportional to 1.69 times the number of edges plus 0 times the number of triangles of y, because triangles don't actually exist in this. However, I then fit the model to the edges and triangles. And this was to test how good the estimator is and how well it can estimate the values. So I did the simulation 200 times with generating and then fitting. And the real value for the edge parameter is negative 1.69. And the mean estimate was about negative 1.5. And this gives us a bias and a mean squared error. The mean squared error is considerably higher than for the triangle parameter, which does not exist. However, I also looked at the significance of the coefficients, and 198 times out of 200, the edge parameter had a value that was statistically significant just using the traditional threshold of p is less than 0.05. Meanwhile, when I look at the triangle parameter, that has a real value of 0, a mean estimate of negative 0.38, and therefore it has this bias. It has a much lower mean squared error, which I did find interesting. And mean squared error is the bias squared plus the variance, meaning that the triangle parameter had much lower variance in the estimate, even if there was a higher bias. So here are histograms of the edge estimates and the triangle estimates. And so with the edge estimates, the actual value is negative 1.69, so around here. We're not quite centered on the correct value, but we're not terribly far off either. And there is a bit of a skew, it's not symmetric. Meanwhile, the triangle estimates are definitely not centered on 0. And there are some really interesting outliers that are just very high magnitude values. And I'm not quite sure why that is the case, but this was definitely not what I was expecting when I did the simulation. What this tells us, though, is that this estimation process is inherently, to an extent, flawed, because we are unable to just do the complete simulation and do the complete solve because we cannot find the parameter or the normalizing constant here. And that is what I have for you all. I'd like to thank my graduate committee for helping me quite a bit. They helped me with the project. They helped me stay on track. Very much appreciate all the effort. And here are the sources I have cited. Are there any questions?
So, actually, first I have a comment. I seeing the new updated version of the simulation where you show the p-values, it worked better than I thought it would. In one way, that it only rejected 3 times out of 200.
That's true. It still, though, I expected the clustering around 0, which we did not
get. Yeah.
Mind you, the variance of the estimate is awfully low.
Mm-hmm.
So you're still clustering fairly close to 0, even if you're clustering a little below 0.
Yeah. Yeah, it didn't often mislead people, though. right?
No,
Because
it did not.
yeah, so that's good. Was that MCMC? Did it use like, or was it the just the pseudo likelihood?
That was MCMC.
Oh, okay.
And so both the generation process was stochastic and the fitting process was stochastic. And so if we go back to like these parameters, then if you run the simulation again, you're going to get slightly different values.
Okay. And just out of curiosity, how long did it take to do just a typical one single run? Not all 200, but just when you
On
run
the order
one.
of roughly a second, maybe a couple seconds, not very long individually.
Mhm. Oh,
But yeah.
So I've got a question. Yeah, let's look at your bibliography here. Is one of these a source where you can find the vocabulary that you are using today?
A couple of them are, yes.
Okay. And is there a textbook that has these different examples, which I must say I found very interesting, that one could go and find more examples of?
I got example works from the StatNet tutorial package, has examples on working through problems
Okay, great.
online. There are textbooks on this subject, although I do not own one at present.
Oh, what are they?
I do not remember their names offhand. I was looking at them a couple months ago.
Yeah. Okay, great. Thank you.
Mm-hmm.
Well, I don't have a question, but that was a very nice talk, Bradley.
Thank you. I very much appreciate that.
I had a quick one, Bradley. You said you had some degeneracy issues with the MCMC.
Yes. So that is something that could affect the simulation potentially, is that sometimes when you simulate, you get thrown like infinity for parameters, or it just fails to converge. And it is possible that the failing to converge or throwing infinity correlates to an extent with what the results are, which would make that the simulation be a little less trustworthy.
This is Margaret. I have kind of a question about how did you do the computing? Were you writing the software yourself to simulate the data sets or to fit the models?
No, I use the StatNet package in R, which is listed here. And it comes with the software and the data sets.
Okay. Some of the questions, if you're doing something that reeks or smacks a little bit of a Bayesian sort of approach, I'd like to find out things like, well, if you're doing one of these and a Markov chain Monte Carlo algorithm, how many iterations do you end up doing, and what kind of, how do you know whether or not the chain is converged? I mean, are there diagnostics that are being performed, something you can look at after the fact to decide whether it's anywhere close to a reasonable, or it's figured out values or trees or whatever that are?
Those do exist. There is a diagnostic that basically throws an error and stops the current running if your simulated model starts diverging too far from the observed data set. It tends to do fewer than 20 iterations, I believe, for the MCMC on this data set. That's just from looking at the R output when I was running this. I do not have any of that handy at the moment, however. This
is something that I'd actually be kind of interested in looking into. What I tell students when they're doing Markov chain Monte Carlo methods for fitting other kinds of models. I mean, it's used for simulating from essentially any probability distribution, not just Bayesian posterior distributions or anything. I tell them, I want to see at least 5,000 iterations, or I'm going to send you back to get more. And you're telling me that it thinks it's done after 20?
I think the 20 might be a measure of something different. I don't exactly remember the output clearly enough at the moment to give commentary on that. It's 20 of something is the maximum. I don't remember what that is exactly, unfortunately.
Okay, thank you.
I will
I guess-
send you like some output and some screenshots of when solving it, and I will spend some time reading through the output more thoroughly myself.
I'd like that.
So I guess I do have one question. I'm sure you touched on this, but I apparently didn't process. In general, what are you trying to accomplish with these models? And what kinds of questions could you answer from what you've done?
What you want to be looking at is why edges occur and what causes them to occur. And so the questions you can look at are, a lot of them are related to social structures in humans. And so you look at a friendship network and you say, are friendships more likely to occur in cycles of given lengths as opposed to just being edges? Are you more likely to have these structures? And so you can do it to observe these things. One case I was reading about was tracking the crossing of firearms illegally across state lines.
Thank you.
Hey, first of all, thank you for the talk. I was wondering if you had done like a broader review of various applications for this, and if you had seen anything in the robotics domain.
I have a bit of a broader overview in my paper. I am not recalling anything in the robotics domain off the top of my head, but I'm sure that you can find some way to do it.
All right, thank you.
So Bradley, and I think this kind of directed at John Gimble as well. There's a guy named Eric Kolazek that has a book on network analysis that I was getting the impression that it was kind of a standard book. Is this one of them that you looked at or worked with? Kolazek?
I didn't work with a textbook. I worked with various research papers and online tutorials for using the software. I would like to purchase the textbook and spend some time reading through it, perhaps over the summer, because I'm just interested in the contents of it.
Which book is that?
I don't remember the name offhand, I'm sorry, but there are textbooks published about this.
Is this the point where all the attendees get dismissed and the committee talks?
I think we're about to that, unless anybody has any more questions.
I think the committee chairs decide at this point what everybody's going to do.
All right, well.
Does anybody have any questions? Any more questions?
Yes, any more questions?
Okay, so if the committee will stay on, and then everyone else, thanks for coming.